Hello everyone, welcome to this lecture on electromagnetic induction. Here is your syllabus. We have almost covered all the topics, and in today's class we will be talking about the Maxwell's equations. So Maxwell's equation is just a group of four different equations, and each equation has its own name. So as you can see in the slide, the first equation is named as the Gauss's law, basically the Gauss's law in electrostatics. The second law, which is known as the Gauss's law in magnetism, some people like to call this, but actually it has no name. I mean, the third equation is known as the Faraday's law, which we have already come across, and the fourth equation is known as the Ampere's circuital law. So these are the group of four different equations which are known as Maxwell's electromagnetic equations, and they have got extreme importance in the field of physics, and they are known as the fundamental equations which give the concept of electromagnetic waves. So what we see in these four equations, these are, by the way, the differential forms of these four equations. There are integral versions also. In the differential form, we have got the first equation as the divergence of the electric field to be rho upon epsilon naught, where rho is actually the charge density or the volume charge density. Then in the second equation, we have got del dot B, that's to be equal to 0. That means divergence of magnetic field is equal to 0. The third equation, which is a Faraday's law, we get the curl of the electric field is nothing but negative of the time derivative of the magnetic field. And in the fourth equation, we get the curl of the magnetic field, which is given by mu naught J plus mu naught epsilon naught, the time derivative of the electric field. So if I have got a changing electric field, then that is capable of giving us a magnetic field. And if I have a changing magnetic field, that is capable of giving us an electric field. So that's what is the beauty of these last two equations. So how to remember this? First of all, we cannot change the order of this equation. For example, if this has been put in number 1, this has been put in number 2, this is similarly in 3 and 4, this order remains intact. Nobody can change this order. All right. So these four equations you have to write repeatedly and practice in your copy so that you remember this. Now we will go one by one to understand how exactly these Maxwell's equations have been derived, or how exactly we get about these equations. Because for example, the Faraday's law, which has been shown in this particular slide, we have not studied it in this form. We have studied in a different form, which says that the magnetic flux linked with a coil, if it changes, in that case there is an EMF induced in that coil, and the EMF is given by the negative time derivative of the electric magnetic flux. So that is a kind of a form that we have studied in case of Faraday's law, but not this particular form. So how exactly this form appears, or how exactly the other forms appears? So we will talk about them in this particular lecture today. So before we go, there are integral form or integral version of these differential equations. So there are two different forms. One is a differential form of this equation, another is an integral form of this equation, and both the forms are equally important. So here I have given a direct correspondence between the differential and integral forms. For example, the Gauss law, if you say, in that case, this is the integral form of the Gauss's law, and which we are more familiar with, that integration E dot ds, which is nothing but the flux of electric field. I can write it as phi E. The E denotes that it is the flux of electric field, which is equal to Q by epsilon naught. So the details about this particular law I will talk in the next slide. Then del dot B is equal to 0. If you write it in integral form, then that gives the flux of magnetic field through a closed surface is going to be 0. So this is basically 0, and this is basically Q upon epsilon naught, where Q is the total charge enclosed by the volume. Now since we do not have any concept of magnetic charges or any magnetic monopoles, so that is why if you have got a small bar magnet within a Gaussian surface, in that case that must give you net amount of flux to be 0. That means the net flux which is going out of the surface will be equal to the net flux coming through the surface. So that is why the change in flux happens to be equal to 0. I'll be detailing about it in a while. Now next is Faraday's law, which gives you the curl of electric field. So that is going to give you this particular equation in integral form, that we have got an integration, rather a complete or uh, full loop integral of E dot dl, the electric field, over some length or some loop basically, that's going to give you the negative time derivative of the B dot ds, that means the flux. Then I have got the final equations, Ampere circuital law. By the way, although I have been calling this to be Ampere circuital law, this is actually modified Ampere circuital law. This is the fourth equation, is modified Ampere circuital law, because Ampere circuital law was framed only up to this, del cross B to B is equal to mu naught J. This is an extra part which has appeared, and this is all the contribution of Maxwell have in this particular set of four different equations. All right, so this looks to be small contribution, but this is the contribution which ultimately completed this theory. Otherwise, previously Gauss's derived one equation, the Faraday's and Ampere's consecutively derived their own equations, but nobody could club them up to form four fundamental equations which could completely define the phenomenon of electromagnetic waves. So that is the reason why you need to have one small modification in the Ampere circuital law, which was otherwise inconsistent. So in today's lecture, I'll be talking about that inconsistency also, how exactly it is inconsistent and why Maxwell thought about that inconsistency and how exactly he removed it. So we'll be talking all about it. So this is actually the integral version of this particular differential form. So these forms are very important. So please take a copy and practice. Until and unless you practice a lot about these equations, you are certainly going to forget about them. Right? All right. So now let us go to each and individual equation or each and individual law separately. So let us first take the Maxwell's first equation, which is the Gauss's law in electrostatics actually. Now what is the statement goes? Statement says the net electric flux through any closed surface drawn in electric field is equal to 1 upon epsilon naught times the total charge enclosed within that surface. This is what is a famous definition we are already acquainted with. So for example, what it says, that if you have got a volume which encloses a charge, say plus q, in that case we know that all electric lines of force will come out through the surface. This is a plus 2 level concept, already we have known about them. And in that case, what is the flux of electric field? That is going to give you the total charge enclosed within the surface or enclosed by the volume divided by epsilon naught. Now, suppose I give you total number. By the way, this Q is the Q enclosed or the total number of charges. Now, suppose I give you a volume where I have got, say, 15 numbers of positive charges, say 16 number of negative charges. In that case, what will be the total charge? Total charge will be 15 plus Q charges plus 16 minus Q charges. So in that case, you find out in this fashion. All right, so this q enclosed will be the total of these charges, not a single charge. All right, so in many of the instances we just show it by plus q, but it is actually the total amount of charge which is enclosed within a volume. Okay, it doesn't matter what kind of charges, it could be positive, negative, or a mixture of positive and negative. You from there find the total amount of charge and then do this calculation, otherwise it will be wrong. I mean, I hope this part is clear. So here is a very brief diagram where you have got some plus q kind of a charge kept over here, shown by the red dot, and the electric flux lines are coming out through the surface. This is a three-dimensional picturization of this event. So flux will come out all through all the points of the surface. All right, so this is basically the integral form, and already we know that we write the flux to be is equal to E dot ds. While I started the chapter on electromagnetic induction, I already have written how exactly we calculate the flux of magnetic field. So it is similar way that we represent the flux to be E dot ds, the electric field multiplied by the surface area or elementary surface area taken as a dot product. By the way, there is a small circle over here. It shows that this is a closed volume, so the surface must be closed. So since we are taking surface integral, it must be a closed integral. Now, how to get the differential form from the integral form or the integral form from the differential form? Let's concentrate on this. So that particular problem has been dealt with in this particular box. So let's consider the differential form, which says del dot E is equal to rho upon epsilon naught. Now I have been repeatedly telling that rho is actually the volume charge density. Now what is the meaning of volume charge density? Volume charge density means rho can be expressed as an integral of Q dV, where dV is the volume, small elementary volume, and Q is the charge, total charge rather, enclosed within this volume. So if you just take an integral of Q dV, you are going to get the volume charge density. So it is basically the charge enclosed per unit volume. Okay. So as we have mass density, which is known as the mass per unit volume. So sorry, I have written a little bit wrong. If you write rho dV, then you are going to get Q. All right. So the charge enclosed can be obtained by integrating the volume density, integrating the charge density over the volume. So as we have mass density to be rho is equal to mass per unit volume, similarly charge density to be charge per unit volume. So in that case, charge happens to be rho into volume, or otherwise in integral form we write it as integration of rho dV. All right. So that's what is the concept of volume charge density. So in differential form, we start with the divergence of electric field, because this is a dot product with the nabla. So we must call it the divergence of electric field, which is equal to rho upon epsilon naught. Now, next step is just integrate on both the side of this equation by volume integral, as I have done in this particular step. So if I take a volume integral on both the sides, I remain with del dot E, that means divergence of some quantity, which is a vector quantity, over a volume equal to 1 upon epsilon naught integration rho dV. Now if you just apply Gauss divergence theorem, what Gauss's divergence theorem says that it's a way to convert the volume integral into surface integral. But the condition is that the volume integral must be in a divergence form. Now that we have here, that the volume integral is in a divergence of electric field, so I can immediately convert it into a surface integral. So I get it, the closed surface integral E dot ds, that's equal to Q by epsilon naught. Now where is actually I have written Q? Q means this, the integration of rho dV. This whole term is actually Q, as already I have said. So this is about the Gauss's law. Now here I have found out a way in which I could find the integral form from the differential form. How to find the differential from the integral form? Exactly the opposite. Just take this down. This is the integral form. Next step, you do this, means convert the surface integral back to the volume integral by applying Gauss divergence theorem. And from there, since you have got volume integral on both the sides, then the integrands, that means the quantities which are remaining within the integral sign, they must be equal. So immediately you get this third step. So from differential to integral form, come down. From integral form to differential form, just do this step upward. Follow the steps upward. Simply it will be obtained. It's a vice versa process. Just 3-step process. You don't have to do much. So this is the beauty of this derivation. So often these kind of questions are asked, that in Maxwell's equation obtain the differential form from the integral form, or vice versa. So how to proceed? In this way you have to proceed. So this is all about the Gauss's law. Next, let us talk about the Gauss's law in magnetism. As already I have said, this particular equation has no name, but many people, because it looks similar to the Gauss's law in electrostatics, so people like to call it as Gauss's law in magnetism. Now what it states? It states that magnetic lines of force are closed or go off to infinity. As already we know, suppose you consider an electric charge, suppose a charge, the electric lines of force coming out of it will go up to infinity, and they will not close on itself. It will go up to infinity. But magnetic field is not like that. Suppose instead of considering a charge, you consider a bar magnet, which already we know. Then bar magnet has got a northern side and has got a southern side. And we know that the magnetic lines of force come out through the northern side and enter through the southern side. And within the magnet, it moves from southern to northern side. So that means the magnetic field lines close on to itself. The magnetic field lines close on itself. These are closed loops. So that is the reason why the number of magnetic lines of force entering and leaving any surface. Here you can see the number of magnetic lines of force entering and leaving any surface must be the same. So in order to explain this, I have drawn this particular diagram. So here you can concentrate. Suppose I have kept a bar magnet within a Gaussian surface. Now you know Gaussian surface is an imaginary surface, and it's just the area it concentrates, or it takes into account the area through which you want to find the flux. So if I consider the magnetic flux over or through the surface which encloses a complete bar magnet, in that case the number of flux lines or the number of field lines of magnetic field coming into this surface must be equal to that flux lines going out of the surface. So this is northern side, so this line will go out of, this line will go, this line will also come out through this surface, this line will also come out. Now see how many lines coming out: 1 2 3 4 and 5. How many field lines going in? This is one, this is one, this is one, this is one, and this is one. So 1 2 3 4 5. So each magnetic line of force which come out through the surface, there is a corresponding magnetic field line which comes into the surface. So that means the total change of magnetic flux is equal to 0. Hence we have B dot ds to be equal to 0. This is in other word to say that magnetic monopole doesn't exist, because even if we know that if you cut a bar magnet, in that case once again you will get a north south combination. So if you cut it into pieces, in that case you will get two different magnets having north and south. You will never get a north pole alone, you will never get a south pole alone. All right, so this is how actually we get. So this is the reason that divergence of magnetic field is always 0, in order to say that the magnetic monopoles doesn't exist. This is what is the physical significance of this equation. Okay, why monopole doesn't exist? Because the provided monopole had existed, in that case we would have got some kind of a flux which would have been there in the right hand side of this equation. But here we see that the flux is equal to 0. The total flux through a Gaussian surface of a magnetic field is equal to 0. That means total number of field lines which is going out of the surface is equal to the total number of field lines coming into the surface. So since the flux is 0, that is why magnetic monopole cannot be there. Magnet will always remain in a dipolar condition. So how to get? Once again, you take the divergence to be 0. I mean, start with the differential form, take the volume integral on both the sides. On the right hand side you don't have to do anything, it's already 0. Just convert it into surface integral by applying Gauss divergence theorem, and you will get the integral form. And if you have to get the opposite, just start with the integral form and go in the upward direction to get the differential form. So this is very easy to deal with, especially the Gauss's law in magnetism and electrostatics are concerned. So let's now go forward to the third equation, or the Faraday's law. Now Faraday's law already we have acquainted sufficiently ourselves. Now what the statement says that when the magnetic flux linked with a coil changes, an EMF is induced in the coil. And that EMF is given by numerically E is equal to minus d phi dt. So I can write a small b over here so that I understand the EMF has been generated by the change in magnetic flux, because electric flux is also involved in Maxwell's equation. So sometime to differentiate between these two, we just write it as a small b or a small e. Now what I can do further, this epsilon, the EMF, is equal to minus d phi dt. Let's write it once again. That is equal to minus d dt of integration b dot ds. Now see, I have written down the flux, and there is no curling sign over here. There is no circular sign. Why? Because this surface may not be a closed surface. That means I am not talking of a volume. This surface is rather an open surface. So that is why the curling is not required, as was required in the case of Gauss's law in electrostatics or magnetism. Alright, so this is an open integral. Now b dot ds is equal to phi, so that is why I have replaced it. Now there is a rule by which if you take this derivative of time inside the integral signs, then it goes in as a partial derivative. So I have taken it in and I have written it as del B del T dot ds. Okay, so I think up to this part it is clear. Now let us try to understand what actually EMF means. EMF means the work done in carrying a unit positive charge completely around the loops. Now suppose you have got a loop or the coil. So if you have a positive charge, what is the meaning of EMF? If you have a positive charge, then what will be the work done required to move it once completely around this loop? That is what is actually the physical meaning of EMF. Now if it is required, so in that case what will be the expression? It will be a circle closed integral E dot dl, the electric field dot the line element. So integration dl basically gives the total length of this loop. Now since we have an expression for EMF and we have converted the flux d phi dt, change of flux with time, as this, if you just equate these two equations or put it, then you will get it like this: closed loop integral of E dot dl minus integration del B del T dot ds. So this is actually the integral form of Faraday's law. Now how to convert it into differential form? Simply apply Stokes theorem. Now Stokes theorem, if you remember, it is a way to convert the line element or line integrals to surface integrals. So how exactly it was there? If you have a closed loop integral or closed loop line integral, then from there you can easily convert to a surface integral, which will take into account the curl of the vector quantity, that is the electric field in this case, dot ds, the area element. So this is actually a surface integral, and on the right hand side I have kept everything to be same. Now see where is the beauty. Here you have got a surface integral on the left hand side, here also you have got a surface integral on the left hand side. So and there is an equal sign, of course. So that is why the integrands, that means the quantities which are within the integral sign, must be equal. So that means del cross E must be equal to minus taken and del B del T. So I can equate them. So if I equate, I simply get the differential form of Faraday's law or Maxwell's third equation. So this is something very important. So this is another way of looking into Faraday's equation. All right. And remember this, I have derived it from whatever known expression, epsilon to be is equal to minus d phi dt, which we have done so far. From there I have converted it into the form of electric field and magnetic field. But there is a difference. What is the difference of this electric field and the previous electric field? I mean the electric field in Gauss's law that you got and electric field in Faraday's law that you have got. There is a difference. Difference is the Faraday's law electric field involves a curl of the electric field, and which is not equal to 0. Now we know that if the curl of a vector field is not to be equal to 0, in that case that vector field is non-conservative, all right, or rotational. It is not irrotational. So how do we know the conservative field and non-conservative field? Conservative field is a field whose curl is actually 0. So if I give you a force field, if you find out the curl of that force field, if it is 0, then it is a conservative force field. So similarly, you take an electric field, if you take the curl, if it is 0, it is a conservative electric field. But in this case, we have got the curl of the electric field is nothing but the rate of change of magnetic field with time with a negative sign. So that is why this field is not a conservative field. This is a non-conservative field. So remember that. This is a very important classification. Alright. On the other hand, if you had the electric field in Gauss's law, if you would have taken a curl of that electric field because of a static charge, you would have got it certainly to be 0 because that's a conservative electric field. Alright. So that's a very basic difference between these two electric field involved in Gauss's law and Faraday's law. Alright, so I hope this part is clear. Next, the most important thing is the Maxwell's fourth equation or the Ampere circuital law. Now, from our knowledge in plus 2 level, we know this definition or the statement of Ampere circuital law to be like this. It states that the line integral of magnetic field around any closed loop is given by mu naught, or the permeability of free space, times the net current I flowing through the area enclosed by the loop. That means if you have got a loop, suppose like this, and see how many current coming out through this. Suppose this is one single wire and current is coming out through this surface in the upward direction. then there will be a magnetic field encircling this current wire, as you can see in this particular diagram. And the line integral of this magnetic field around this loop is given by mu naught into the current I. So this is a closed loop line integral. Why closed loop? Because the magnetic field will curl onto itself. So if you frame a single loop, then you will see the loop is complete loop. That there is no joint kind of a thing. It's a complete loop. There is no breakage of continuity. So that is why the closed loop integral of magnetic field is equal to mu naught I. By the way, although I have written it in bold face, which itself means it's a vector quantity, but you can explicitly show also. Alright, this is what is an ampere circuital law. If you try to convert it into the differential form, how would you start with? You will start with integral b dot dl to be equal to mu naught I. Now I is expressible as the surface integral of current density, because we know what, that current density J is nothing but I by A. A is a vector quantity, that means area. So if you just forget about this vector and just take the magnitude, in that case you will write it as I to be equal to J into area, or I can write area to be S because I have been writing it so. So in integral form, how can you write? You can write it as J dot ds. So since you can write the current expression as J dot ds, you just replace it in its position and you get this. Now once again, this is a surface integral, this is a line integral, you cannot equate. So in order to do an equation, you have to apply Stokes theorem. That means you convert this line integral into surface integral. Now remember, I have been applying Stokes theorem only when there is a closed loop line integral. This is important. I hope you are aware of this fact from your mathematical physics courses. When you have got only a closed loop integral of certain vector quantity, then only you can convert it into a surface integral, not otherwise. So once you have converted into surface integral, you remain with a surface integral on both the sides, and you can equate the integrands. That means del cross B to be equal to mu naught J. So this is the differential form of Ampere circuital law. So this is all about Ampere circuital law, but this law is sort of inconsistent, and the inconsistency was pinpointed by Maxwell, and that's what gives the Maxwell's modification to this particular law. Let's see about that. What is this modification all about? Now Maxwell just did one single operation, and that operation is he simply took divergence of this particular thing. So Ampere circuital law gave us del cross B to be equal to mu naught into J. So what Maxwell did, he took divergence on both the sides. So he got this divergence of del cross B, that's equal to mu naught divergence of J. Clear? Now there is a law which says the divergence of a curl is 0. That's a very basic thing. You can try it for yourself also. So you will get always the divergence of a curl is 0. So that is why the left hand side means this quantity will always go off to 0. But the right hand side, where you have got a del dot J term, that means divergence of the current density term, this always doesn't go to 0, and this is because of the continuity equation, which says del dot J to be equal to minus del rho del T. Once again, rho is the volume charge density. That means if you have got a rate of change of volume charge density, that is nothing but equal to the divergence of the current density. So Maxwell was little bit puzzled, because if an equation has to be consistent under certain operation, what is that operation here? Divergence operation. I have taken divergence on both the sides of this equation. So one side was giving me 0, but other side after taking divergence was giving me certain kind of a value. That means that is minus del rho del T. So that is why there must be some kind of an inconsistency in this equation. That was the first thing that pointed out Maxwell. Now how to remove this inconsistency? So this is the part where we will remove this. So removal of inconsistency. How to remove that? Maxwell once again brought the concept of Gauss's law. in electrostatics. That is del dot E to be is equal to rho upon epsilon naught. So that implies what? That rho is equal to epsilon naught del dot E. So if you just put it over here, del dot J to be is equal to minus del rho del T, that means this particular equation, and in place of rho I write this, then I get epsilon naught taken common, or epsilon naught let it remain, just take this time derivative within, so you will remain with minus del dot epsilon naught del E del T. Alright, so I have taken this divergence thing common willingly so that I can bring this particular term to the left hand side along with J. So that's something that we will go in the next slide. So here you see I have just brought this particular term to the left hand side along with J, so that I get del dot J plus epsilon naught del E del T, which is to be equal to 0. Now this term which you have got recently, this is the total current density term. That means in the Ampere circuited law, this particular term was missing, and because of which the equation was coming out to be an inconsistent one. Alright, so Maxwell did this small modification and brought this term, or connected this term with the actual current density J. Alright, and this will certainly remove the inconsistency, because now if you take a divergence operation, divergence of this total current density term happens to be 0 from this equation. Alright, so now Ampere circuited law has been consistent, but with the addition of an extra term which is epsilon naught del E del T. Now what this term all about? This term is nothing but known as the displacement current. So this modification, now these lines, these few lines are important. This is ultimate equation, the fourth equation of Maxwell, that curl of magnetic field is equal to mu naught J plus mu naught epsilon naught del E del T. Now this modification does not change anything so far as the magnetostatics is concerned. That means whenever the electric field E is constant. Because if electric field is constant, it doesn't change with time, then this part goes off to 0 and you remain with the original form of the Ampere circuited law. So we still have del cross B to be is equal to mu naught J. In fact, the Maxwell's term is hard to detect in ordinary electromagnetic experiments. This term is not easily detectable. It usually competes with the J. That means this is the original current density with which the second current density term competes for due attention, and hence no one could detect it in the laboratory. For example, Ampere did some experiment, Faraday did some experiment, but nobody was aware of this presence of this extra term del E del T. Why? Because whenever you perform an electromagnetic experiment, the dominant contribution appears from this particular term mu naught J, and mu naught epsilon naught del E del T, this particular term remains a dormant one. So that is why nobody could give due attention to this particular term. It is only theoretically that this term was predicted. So that is why, however, it plays a crucial role in the propagation of electromagnetic wave. Because Maxwell was working on the propagation of electromagnetic waves, or he was working on the very nature of electromagnetic waves. So that is why he could discover this particular thing. And this extra term is known as displacement current, and actually it has got the dimension of current density. If you just put the units of electric field and the permittivity of free space epsilon naught and just do some calculation, in that case you will see that this is giving you the expression for current density, that means current per unit area or ampere per meter square kind of a thing. So this displacement current has nothing to do with real current. Remember, this is one of the most important statement. Displacement current is not a real current that flows through a wire. No, this is only added so as to make the Ampere circuited law consistent one, number one. Number two, it is a current only in the sense that it can give you magnetic field, or it can generate magnetic field. So a changing electric field with time generates a magnetic field. So in that sense, it's a current. It's not a real current that flows through, or that you will detect through an ammeter in while doing an experiment. All right, so this is the concept of displacement current. I'll be talking about displacement current even more. So characteristics of displacement current, this particular thing you should remember. It has the same unit as electric current density. Displacement current is a current only in the sense that it produces magnetic field. It has none other properties of current. For example, displacement current can have a finite value in vacuum where there are no charges of any type. In vacuum, if you do an experiment, see, in vacuum you do not have any charge. But even then, there might be some electric field which change, because you know electromagnetic light is an electromagnetic radiation. It comes from sun to the earth. So there must be changing electric field. So that electric field change will be responsible for generation of the magnetic field. And that is the reason why we have an alternating electric field and magnetic field perpendicular to each other oscillating, and that is that gives rise to the electromagnetic radiation. This is something already we know. So how come this magnetic field is generated? Only because of this displacement current. So it serves to make the total current continuous across the discontinuities in conduction current, and it makes the Ampere circuital law a consistent one. So these are few properties of this displacement current. All right. Now there is a very interesting story. Why the name displacement current is there? Maxwell could have told it as anything. Maxwell could have come up with a name like it's a Maxwell's current. Normally we do so. We have seen many people to do so, many scientists to do so, to coin something, a newly discovered thing after his name. But he didn't give that name. Why? It's because there is an interesting story. Maxwell came up with this rather curious name of displacement current because many of his ideas regarding the electric and magnetic fields were completely wrong. Why? For instance, Maxwell believed in the presence of an ether. You remember that whenever we are talking about special theory of relativity, there I told that there is a medium called ether, which at that time was supposed to pervade all space. But later on we came to know that there is nothing called ether. And Maxwell thought that electric and magnetic fields were some sorts of stresses in the medium. He also thought that displacement current is associated with displacement of the ether medium. So actually, Maxwell thought that displacement current is responsible for displacement of some ether particles. Okay, so whenever electromagnetic radiation will propagate through ether medium, in that case it will displace or cause to displace some of the ether particles. So that is why this unusual name was coined, that displacement current. All right, although we today know that there is nothing called ether, but the name remained. All right, this is a very interesting story. I have also given you this link from where I have taken this, so please you can go and just see this for yourself. All right. So physical significance of Maxwell's equation, this is all very important thing. Many a times you are asked to write the physical significances of Maxwell's equation. So please go through this slide by yourself. I don't intend to explain it one by one or line by line. These are very easy thing already which we have explained about. Basically, it consists of the four different equations that we have studied in Maxwell's equation, and talking about those four different equations. That's what gives the physical significance of Maxwell's equation. All right, so that's all I had in this particular lecture. So in the next class, maybe we will talk about something more on this Maxwell's equation and displacement current, how exactly displacement current problem can be tackled. Today we have tackled it theoretically by taking a divergence operation of Ampere's circuital law on both the side and showing that there is an inconsistency, and finally removing that inconsistency. But there is a real life problem, capacitor problem, which can be thought, and in that problem also we will see there will be an inconsistency if we just apply Ampere's circuital law. All right, so that should also give us modification. So that we will talk up in the next class, and some part of continuity equation which we have dealt with in today's class, that is del dot j2 b is equal to minus del rho del t. This equation also I will talk about, and how exactly, what is the origin of this equation, this also I'll be talking about. All right, so that's all I had in today's class. Thank you.